In this example, we are going to be constructing a conical paper cup from a circular sheet of paper. So the idea is that we have some sheet of paper. So let me make that circular. Okay, so we have a sheet of paper like this with a certain radius r. So we have a sheet of paper with radius r. And then of course we're going to remove a section. Let me see. So we're going to remove a section of that piece of circular sheet of paper. Like this. And so we're going to remove this strip right in there. So this is going to be cut away. And then we'll have a circular wedge, and we're going to glue this edge right here to that edge right there, and then thereby creating a three-dimensional cone. Something like that. Okay, so we need to figure out how to do this in order to maximize the volume of the resulting cone. Now I haven't done this problem in advance, so you'll get to see, kind of all of the brainstorming that goes behind, solving a problem like this. First of all, I'm thinking we need some sort of control variable, right? We have to make a decision at some point, and based on that decision, we'll end up with a cone. So the control variable is naturally this angle right here, theta. So that's not stated in the problem statement, but let's define theta to be the angle of the wedge that we remove from the circle. So let theta represent the angle of the wedge that we remove from the circle. Always get in the habit of defining your variables and writing down what they mean. So theta is this angle right there. Now, in order to come up with the volume of the cone, the volume is going to be given by 1/3 pi r squared h. So the volume of a cone is 1/3 of the base area times the height. So somehow in the base areas, we'll call that lowercase r, and then the height is h. So lowercase r is the base area of the cone, or the base radius of the cone, and then h is the height of the cone. Now, once we select theta, that's going to, in our mind we can see it. If you have a circular sheet of paper and you cut a certain angle away from that paper and glue the edges together, it will create a definitive cone. And that cone will have a certain base radius and a certain height. Now, part of the challenge of this problem is how do we figure out what the base radius and the height of that resulting cone are in terms of theta? So how do we express that mathematically? Obviously we can take a specific sheet of paper, cut the wedge out, fold it, and measure the area or the radius of the base and the height. But how do we actually go about expressing this mathematically? Well, first of all, in my mind, I'm seeing a way that we can figure out lowercase r. So lowercase r is going to be related to the circumference of the base of the cone, right? So the circumference of the base, if I travel around the base of this cone, the circumference is going to equal 2 pi little r. But that circumference is exactly equal to the arc length of the paper, minus the arc length of the wedge that I removed. And so what is that length? So if we have this length in terms of theta, we can then represent the circumference of the cone in terms of theta. Well, the arc length that was removed, so this arc length right here, is going to be given by r times theta. So theta is in radians. We want to use radians. And recall that the arc length of a circle, when an angle is measured in radians, the arc length, the corresponding arc length is just equal to r times theta. In fact, that's the definition of radians, if you will. Because a full circle, theta is going to have a value of 2 pi, so the full circumference is 2 pi r. So therefore, the missing, or the remaining arc length is going to be 2 pi r minus theta r. So the arc length here is equal to 2 pi r minus theta r, which means the circumference of this cone, because this section right here make up the circumference of the cone. So 2 pi lowercase r is going to equal 2 pi minus theta all times capital R, or 2 pi capital R minus theta capital R. So this is the circumference of the base of the cone. This is the circumference of the circle minus the arc length of the missing section. So lowercase r, in terms of theta, we can divide by 2r. So we get r is equal to capital R minus, okay, so I'm going to use the first form where I have the capital R factored out. So it's going to equal 1 minus theta over 2 pi times capital R. Right, so I took essentially this equation right here, divided by the 2 pi. 2 pi over 2 pi is 1. Theta over 2 pi is like this. So lowercase r is equal to quantity 1 minus theta over 2 pi times capital R. So it's literally, the ratio is literally what fraction of the circle is remaining. And that basically the radius is reduced by that factor. So that's an equation that we have to relate the radius of the cone in terms of the angle theta. Now we somehow have to get the height of the cone in terms of theta. So let's see, how can we do that? So how can we figure out the height of this cone in terms of theta? What's the easiest way? So this radius here, capital R, is going to equal what's called the slant height of the cone. So that length down that side is going to be exactly here, because when we glue this edge with this edge, this is going to just become a straight line from the vertex of the cone to the base. So h is going to be given by the square root of capital R squared minus lowercase r squared. And we already have r as a function of capital R. So this might turn out to be interesting. So what happens if we square r? So lowercase r squared, well, r is also equal to capital R minus theta over 2 pi times capital R. So this is going to be, or we can write it like this. So if we square 1 minus theta over 2 pi, we get 1 minus theta over pi plus theta squared over 4 pi squared, all times capital R squared. So that is r squared as a function of theta. So just expanding this by squaring it. We get 1 squared minus twice the product of this and this, which is just equal to minus theta over pi, and then plus this term squared. So plus theta squared over 4 pi squared. Now when we do capital R squared minus this, notice that the first term here is just equal to capital R squared. So we get capital R squared minus capital R squared. So therefore capital R squared minus little r squared is going to be theta over pi minus theta squared over 4 pi squared times capital R squared. So h is going to be equal to the square root of theta over pi minus theta squared over 4 pi squared, and then times this capital R. So now we have kind of the main ingredients to go about solving this problem. We have the height as a function of theta, and we have the radius of the base of the cone as a function of theta. And we can combine those into the formula for the volume of a cone to find the volume strictly as a function of this angle theta, like that. Okay, so I think we can safely remove this stuff. and all of this. So the volume of the cone is 1/3 pi r squared, so it's this squared. So it's 1 minus theta over 2 pi quantity squared times capital R squared, and then times height. So then times the square root of theta over pi minus theta squared over 4 pi squared times r, capital R, so that makes that capital R cubed. So basically capital R cubed pi over 3 times 1 minus theta over 2 pi times the square root of squared of theta over pi minus theta squared over 4 pi squared. Now that's interesting because recall that the part inside of the square root was given by 1 minus theta over 2 pi squared. Right, so that this stuff inside the square root was equal to this. Just wondering if I can simplify this any further before taking derivatives. Let's see, what can we do with this? So can I bring this inside of the square root? I guess I can. I have the same 1 minus theta over 2 pi. Yeah, recall this was, the cone. We had h, little r, and capital R. So we have capital R squared minus little r squared, and there was the common capital R that got factored out. So it was just really 1 minus this thing squared. If we bring this in, we would have to be to the 4th power, and we would have something to the 4th minus something to the 6th. Not sure if that would be a simplification. Okay, I thought about it for a few minutes, and I don't see any obvious way of simplifying this any further. So we just have to go ahead and start taking derivatives and see where that takes us. Okay, so this is basically the function that we're trying to optimize. So we'll move that all the way up here. Perfect. Okay, so when we take the derivative of this, we're going to need to use the product rule. So that's going to be this term times the derivative of this plus this times the derivative of that. And the coefficient up front is, just going to be here the whole time. So let's actually define this piece to be f of theta. And then v will be pi r cubed over 3 times f of theta. So let's define f of theta is equal to that stuff in red. 1 minus theta over 2 pi squared times the square root of theta over pi minus theta squared over 4 pi squared. Yeah, notice that theta, okay. Yeah, okay. All right, so let's go ahead and differentiate. So f prime of theta. Okay, so let's do the derivative of this guy out front first. So it's going to be 2 times this stuff. That's a pi. To the 1, and then times the derivative of the inside. Now the derivative of the inside is minus 1 over 2 pi. So when we multiply by negative 1 over 2 pi, the 2 cancels. So 2 over 2 is 1. So we just get minus 1 over pi. So we get a factor of minus 1 over pi. And then it's just times this second guy. So times the square root of pi over theta minus theta squared over 4 pi squared. So that's this term times the derivative of the first term, and the derivative of the first term is right here. So this term we differentiated, the 2 comes down, we get 2 times this to the 1, and then times the derivative of the inside, which is minus 1 over 2 pi. So 2 over 2 pi is 1 over pi, so we get minus 1 over pi times this. Okay, so next we get plus this term, so plus this first factor right here, so plus 1 minus theta over 2 pi squared times the derivative of this stuff. Now this is something square root, so the square root of something. Remember the derivative of square root of x was 1 over 2 square root of x. So this is going to be 1 over 2 square root of this stuff. Theta over pi minus theta squared over 4 pi squared. And we multiply this by the derivative of the inside. So we're going to multiply this by the derivative of the inside function. So the derivative of the inside is 1 over pi minus theta over 2 pi squared. Because the 2 comes down when we take the derivative of theta squared, we get 2 theta. 2 over 4 is 1 over 2, so we get theta over 2 pi squared. So that is, so this stuff right here is the derivative of that second factor, and then this is just the first factor repeated. So this, to find the critical points, all of that has to equal 0. And of course, our domain is thetas from 0 to 2 pi. Okay, so we made progress. Maybe it doesn't feel like that because this is not a pretty equation. I suppose beauty's in the eye of the beholder. But we can actually do some stuff with this. So it's this minus this, right? We have a minus sign on the first term, so it's this term minus this term. And when we have this minus that equals 0, that means this has to equal that. So that's the first thing. This term is equal to, without the minus sign, equal to this stuff. So this is equal to that. It balances out because their difference has to be 0. Secondly, we have these yucky square roots, but observe that on the second term, we have 1 over the square root, and then on the first term, it's just a square root. So the mental math part is, okay, this minus this equals 0, so that means this is on the balance with that. This stuff right here, aside from the minus sign up front, is equal to this stuff right here. So this is equal to this. And now the square root will bring up over here, the square root times the square root is just the original 1. So this stuff simplifies to 1 over pi times 1 minus theta over 2 pi times theta over pi minus theta squared over 4 pi squared, and that's equal to the numerator here. And in fact, we have a 1 over 2 here. That's okay, 1 over 2 times 1 minus theta over 2 pi quantity squared times 1 over pi minus theta over 2 pi squared. Okay, so that's equal to that. So let's see, we have, what type of equation is this? We have a cubic, so theta times theta squared is theta cubed, and then here we have a theta cubed. So it's potentially not an easy equation to solve, but let's see if we can kind of simplify this in any way. First of all, we can kick the 2 over here and the pi over there. So basically we can cross multiply. So there was the 1/2 here, so 2's right there, and there was 1 over pi here, so pi goes up here. Okay, so 2, what is all of this stuff? Let's FOIL. So let's start with the cubic terms. So theta cubed over 8 pi cubed. So it's theta cubed over 8 pi cubed. And then the square terms, we get minus theta squared over 4 pi squared. So that's these two. And then we get 1 times this, so that's minus theta squared over 4 pi squared. So one factor, or one term of this comes from right here. We get minus theta squared over 4 pi squared. And we also get this one right here, minus theta squared over 4 pi squared. And then finally plus theta over pi. And of course, these two can combine, and we can get 2 theta cubed over 8 pi cubed minus theta squared over 2 pi squared, right? 1/4 plus 1/4 is 1/2 plus theta over pi. And this is equal to pi times, okay, if we square this, we're going to have, so this one's going to be 1 minus theta over pi plus theta squared over 4 pi squared. So this pi, let's bring that into here and we get cancellation, pi over pi, pi over pi. So that pi can then go like this. So it's 1 minus theta over 2 pi, right? Because we get pi over pi and then pi over pi squared. So we just get 1 minus theta over 2 pi for the second term. So I've factored that factor of pi into this second term. So then the whole thing, now if we're lucky, which we might not be, but if we're lucky, the theta, something will cancel out and we'll be able to actually solve this. Okay, so the theta cubed term comes from here. So the theta cubed term on this side is going to be minus theta cubed over 8 pi cubed. Okay, and then for theta squared, it's going to come from this and from that. Okay, so what are the two theta squared? Theta squared, we get theta squared over 4 pi squared, and then plus theta squared over 2 pi squared. So 1/4 plus 1/2 is 3/4, so it's plus 3 theta squared over 4 pi squared. Right, that comes from here and from there. Okay, so we got the theta cubed term from here to here, theta squared from there and from there. Now theta term from basically two places, change color a little bit, from here and then from there. So that we get minus theta over pi times 1 and then minus theta over 2 pi. So that's minus theta over pi minus theta over 2 pi, so that's 1 plus 1/2, that's 3 theta over 2 pi, and then finally plus 1. Okay, well at least we're approaching an equation here, even though unfortunately this theta cubed terms do not cancel out like I was hoping. Let me factor in this 2 over here. So 8 becomes 16, 2 becomes 4. No, wait, this 2 was up here. So this 8 becomes 4. This 2 becomes 1. And this becomes 2, like that. Okay, so now we just have to combine everything on one side. So moving this, everything to the left-hand side, 1/4 plus 1/8 is 3/8. So we get 3/8 theta cubed over pi cubed. And then the squared terms, subtracting this, we get basically 1 minus 3/4, so that's minus 7/4 theta squared over pi squared. And then this one, this guy moves over, 2 plus 3/2 is finally plus 7 theta over 2 pi is equal to 0. Now notice that we can actually say that this is 3x cubed minus 7x squared plus, oh, and then there's a 1 there, isn't there? So then minus 1 equals 0. So minus 7x squared plus 7x minus 1. Now what did I do? I set x is equal to theta over 2 pi. So notice that I have theta cubed over 8 pi cubed, 8 is 2 cubed, theta squared over 4 pi squared, and theta over 2 pi. So I have this common theta over 2 pi showing up. So if I define x to be theta over 2 pi, I just get this equation right there. I suppose that substitution, replacing theta with theta over 2 pi up here, would have probably simplified some of this work. But let's see if we get any root that might be of interest. So let's say f of x so f of x is 3x cubed minus 7x squared plus 7x minus 1. Plot f of x equals 0 to 1. So yeah, so there's the root right there. So basically that root is going to correspond to the critical point of the function that will maximize the volume. So if you have a graphing calculator, you can plot this equation on the interval from 0 to 1, and then that gives you the value of x. So theta will just be 2 pi times that value of x, and then you would plug in that value for theta for the original volume equation, and that would give you the maximum volume. So a little bit of a little bit of a technical mess here, but it's with the derivative rules you can actually get to the answer, and then basically you can show that the maximum volume occurs when you have a root of this simple cubic polynomial down there. So I prefer problems usually when you can take a few extra algebraic steps and actually algebraically solve, but with the aid of a graphing calculator you can solve for the roots of this and then find the maximum volume that way.